This lesson explains how to solve problems with three similar right triangles. In the investigation that you just completed, you discovered that the altitude to the hypotenuse of a right triangle divides the right triangle into two right triangles that are similar to each other and the original triangle. The altitude, length h, to the hypotenuse of a right triangle divides the hypotenuse into two segments, lengths p and q, such that P over H equals H over Q. We will explore how to solve problems like this in the next several slides. We're going to learn a new definition that's going to help us solve problems like this when we have three similar right triangles. The geometric mean of two positive numbers, A and B, is the positive number such that A divided by X equals X over B. What we're going to discover in three similar right triangles is there are several geometric mean relationships based on this picture. Before we do that though, let's review the triangles that are similar. So if we look at the big triangle, let's look at the big triangle, triangle ADC, which is the very large triangle. We know that triangle ADC is similar to triangle A because they both share A, and then we need to go to the right angle, ABD. Okay? We also know that triangle ADC, which is the big triangle, is similar to triangle. Now, since we start with ADC, we need to start with triangle D. Then we need to go to the right angle, which is B, and then we need to go to C, which they share. Now, this is what you did in the investigation. Since triangle ADC is similar to triangle ABC and triangle ADC is similar to DBC, we can say that triangle ADC is similar to triangle ABD, which is also similar to triangle DBC. Now that we've established the three similar right triangles, we need to look back at the geometric mean. If you look at the geometric mean proportion, you notice that x appears in the denominator and the numerator of the proportion. In order to have a geometric mean relationship, you need the geometric mean, which is x, to occur twice, once in the denominator and once in the numerator. We're going to set up our proportionality statements, and we're going to look at the geometric mean relationships in three similar right triangles. So we're going to first look at triangle ADC and its similarity to triangle ABD. We can write the proportionality statement based on the similarity statement. So the proportionality statement is AD divided by AB equals DC divided by BD, which equals AC divided by AD. Now, when we look at this proportionality statement, we discover that AD, which is up here and here, occurs twice in our diagram, which means that AD is the geometric mean between AB and AC. Because if you separate the proportion, you have AD divided by AB equals AC divided by AD. Since AD occurs twice, once in the numerator and once in the denominator, it's the geometric mean between AB and AC. Now that we have determined one geometric mean relationship, let's look at the similarity statement between ADC and DBC. So if we have ADC is similar to triangle DBC, let's set up the proportionality statement for this similar triangles. So AD divided by DB equals DC divided by BC equals AC divided by DC. Now in this situation, we noticed that DC is in the numerator and the denominator in this proportion. So it occurs twice. So DC is the geometric mean between BC and AC. Because if you look at the proportion, DC divided by BC equals AC divided by DC. DC occurs twice in the numerator and the denominator when you look at this part of the similarity statement. The last geometric mean relationship we're going to look at is going to be between ABD and triangle DBC. So we have triangle ABD is similar to triangle DBC. That's the similarity statement. So let's write the proportionality statement. So AB divided by DB is equal to BD divided by BC is equal to AD divided by DC. When we look at this proportionality statement, we discover that DB, which is also BD, is in the denominator here and in the numerator here. So our geometric mean relationship is BD is the geometric mean between AB and BC. Because remember, if you look at the proportion, AB divided by DB equals BD over BC, and here's DB and BD, same thing, occurring twice. We just discovered that BD is the geometric mean between AB and BC, DC is the geometric mean between BC and AC, and AD is the geometric mean between AC and AB. Well, what does this mean? The first thing I want us to do is let's circle every single geometric mean relationship. So BD in our picture is H, which is our altitude. DC is B, and AD is A. Notice how our three geometric mean relationships are the altitude and the two legs of the big right triangle. Now let's look at the geometric mean relationships between the sides. So BD, so I'm going to circle BD again in red. BD is a geometric mean between AB and BC. AB is the side right here, and BC is the side right there. So AB, which is H, is the geometric mean between Y and X. So let's write that as a proportion. So remember, geometric mean occurs twice. So H has to be in the numerator and H has to be in the denominator. And it's the geometric mean between Y and X. Y and X. If you notice, this is what you looked at in the investigation. H is the altitude of the big triangle, and it's the geometric mean between the two parts of the hypotenuse. It will always be this case for three similar right triangles. Let's look at DC. DC is right here, which is B. B is the geometric mean, which is DC, between BC, which is this small part of the hypotenuse, and AC, which is the entire part of the hypotenuse. So notice how X, which is the closest side, which is BC, B is the geometric mean between X and C, which is the entire thing. So remember, geometric means occur twice. So I'm going to put B in the numerator and the denominator. And then it's the geometric mean between X, which is the closest side, and the entire hypotenuse of the big triangle, which is C. Okay? The last geometric mean relationship is AD, which is A. So I'm going to go up here and recircle A in green. It's the geometric mean between AC, which is the entire hypotenuse, and AB, which is its closest side. So if you look and you draw a picture, it's the geometric mean between its closest side, which is AB, and the entire hypotenuse, which is AC. So remember, it occurs twice. So we have A. A occurs once in the numerator, once in the denominator, because it's a geometric mean. And it's the geometric mean between its closest side, Y, and the entire hypotenuse, which is C. These are the three geometric mean relationships that happen in every single similar right triangles. Now we're going to do some examples that explore these ideas. The first thing you're going to do when you see a problem that contains three similar right triangles is circle what represents the geometric mean. Remember, the geometric mean is the altitude and then the two legs. We don't need that right now because those aren't variables. So the altitude is the geometric mean between the two closest sides of the hypotenuse. So in this case, 9 and 3. Because it's a geometric mean, we're going to write what we've circled twice. So x is in the numerator and the denominator. And it's the geometric mean between 3 and 9. So we have 3 and 9. Now once we have that set up, we're going to solve that proportion. So we have x times x, which is x squared, equals 3 times 9, which is 27. Now we need to solve for x. So x equals plus or minus the square root of 27. Now we're going to break up the radical. This is where all the radical stuff comes back. So 27 is 9 and 3, and 9 is 3 and 3. So we have x equals plus or minus the square root of 3 times 3 times 3. 3 is going to break out. So we have x equals plus or minus the square root of 3 root 3. Now, since x is a length of a side and lengths are always positive, our final answer is x equals 3 square root 3. In this example, which is the same picture as before, we're looking for a different length. We're looking for y, which is one of the legs of the big right triangle. Now remember, y is the geometric mean between its closest side, which is 3, and the entire hypotenuse, which in this case is 9 plus 3, which is 12. So since y is our geometric mean, we're going to circle it, and we're going to put it twice in the proportion. So y is in the numerator and y is in the denominator. Now it's the geometric mean between 3, which is the closest side, and the entire hypotenuse, which is 12. So now we're going to solve this proportion. Y times y is y squared. 3 times 12 is 36. Now we're going to take the square root of both sides, so y equals plus or minus the square root of 36. Square root of 36 is 6, so plus or minus 6. Since lengths are always positive, y equals positive 6. We are now going to do another example using these ideas. We have three similar right triangles because we have three triangles with two right angles. So since we have three similar right triangles, we need to first circle our geometric mean. So our geometric mean is the altitude and the two legs of the big right triangle. So 10 is our geometric mean. Now it's the geometric mean between its closest side and the entire hypotenuse. That is always true for the legs. So in this situation, it's the geometric mean between x and the whole hypotenuse, which is x plus 21. So we're going to solve this by first setting up our geometric mean proportion. So 10, because it's the geometric mean, occurs twice. And it's the geometric mean between the closest side, which is x, and the entire hypotenuse, which is x plus 21. Now, once we have this proportion, we need to solve for it. So we have 10 times 10, which is 100, equals x times x plus 21. Now we need to distribute. So we have 100 equals x squared plus 21x. This is a quadratic equation. So the way we solve quadratic equations is we set them equal to 0 and factor. So let's go up here. So we have x squared plus 21x minus 100 equals 0. So I'm going to factor this. So we have x and 25 and 4, and we have positive 25 and negative 4. So now we're going to tee it up. We have x plus 25 equals 0, and x minus 4 equals 0. So x equals negative 25, and x equals 4. Now we know that lengths have to be positive, so we need to take these values and plug them back in. So when we take negative 25 and we plug it back in, we discover that this x would be negative 25, which doesn't work because lengths need to be positive. So we need to reject the negative 25. But when we take 4 and we plug it back in, we get a positive 4 here, and that works for this situation. So x equals 4 is our answer. In this example, we're going to combine all the ideas that we just did in separate examples. So we're going to look for x, y, and z in the following diagram. In all problems with three similar right triangles, first always go through and circle the things that represent the geometric mean. So y, which is a leg, 6, which is the altitude, and z, which is the other leg of the big right triangle, are our three geometric mean relationships. So y, which is the leg, is the geometric mean between its closest side and the entire hypotenuse, which is x plus 9. So that's not going to be a helpful one to start with because we have two variables. So let's look at 6. 6 is the geometric mean between its closest part of the hypotenuse and the other part of the hypotenuse. Aha! So this is probably where we should start. So 6, which is the geometric mean, occurs twice. So we have 6 and 6. And it's the geometric mean between the two parts of the hypotenuse, so x and 9. So x, which is one part of the hypotenuse, and 9, which is the other part of the hypotenuse. When we solve this proportion, we have 9x equals 36, so x equals 4. So now that we have x equaling 4, we know that the big hypotenuse is 13, and that should help us with our other geometric mean relationships. So as we stated before, y, which occurs twice, is the geometric mean between its closest side, in this case is 4, which we just found, and the whole hypotenuse, which is 13. So we have y times y, which is y squared, equals 4 times 13, which is 52. So we have y equals plus or minus the square root of 52, 52, not 54. When we break out the radical, we have y equals plus or minus 2 root 13. Since lengths are always positive, y equals 2 square root 13. Now our last geometric mean relationship is z. Z is the geometric mean between its closest part of the hypotenuse and the entire hypotenuse, which is 13. So z occurs twice, because it's the geometric mean relationship, and it's the geometric mean between its closest side, which is 9, and the entire hypotenuse, which is 13. So when we cross multiply, we get z squared equals 9 times 13, which is 117. When we break up our radical, we have z equals plus or minus the square root of 117. 117 is 3 times 3 times 13, so our 3's break out. So z equals plus or minus the square root of 3 root 13. Since lengths are always positive, z is the square root, z equals 3 square root of 13, positive 3 square root 13. This last example has three similar right triangles, and then another problem that deals with the angle bisector. These ideas are often confused because they both contain three triangles, but it's really important that you understand that three similar right triangles is not the same as an angle bisector that creates two triangles that have a proportional relationship. So let's look at this first problem. This first problem we know contains three similar right triangles because here's the right angle and here's the right angle. Okay, so that means we have three similar right triangles. So our geometric mean relationship is the leg. So in this case, 15. 15 is the geometric mean between its closest side, which is 9, and the entire hypotenuse, which is x plus 9. So since 15 is the geometric mean, it occurs twice. So we're going to put 15 in the numerator and 15 in the denominator. Now it's the geometric mean between its closest side, which is 9, and the entire hypotenuse, which is x plus 9. Now we're going to solve this proportion. Now we could just cross multiply, but these numbers are a little big. So when the numbers are big, I like to simplify the proportion if I can. So 15 divided by 9 simplifies to 5 over 3, and that equals x plus 9 over 15. Now we're going to cross multiply. So 15 times 5, I think it's 75. 15 times 5 is 75. And then we have 3 times x plus 9. So we have 75 equals 3x plus 27, We're going to subtract the 27 to both sides. So we now have 3x equals 75 minus 27, which is 48. And then we're going to divide both sides by 3, so x equals 16. That's our first example. Now over here, we do not have three similar right triangles. Because we have this angle marking right here, we have an angle bisector. So this is the angle bisector that bisects these two sides. So this means that because we have an angle bisector, it divides this and this proportionally to this and this. Okay, those are our proportional sides. So we'll call this y. We don't know what it is. So we know that 12 divided by 9 equals x plus 5 divided by y. Now we have two variables, so that's a little tricky. So let's figure out what y is. So we know that x plus 5 plus y equals 14, because 14 is the entire length of this side. So we can say y equals 14 minus x plus 5. So we'll keep simplifying. So we have y equals 14 minus x minus 5. So y equals, looks like 9 minus x. So we'll return over here and substitute in. So we have 12 divided by 9 equals x plus 5 over 9 minus x. Once again, I think it's a good choice to reduce this proportion. So 12 divided by 9 reduces to 4/3. So we have 4/3 equals x plus 5 over 9 minus x. Let's cross multiply. So we have 4 times 9 minus x equals 3 times x plus 5. So we have 36 minus 4x equals 3x plus 15. Let's go up here. And we end up with, let's do 36 minus 15. Sorry about that, is 21. And then we have 3x plus 4x, which is 7x. And then when we divide both sides by 7, we get x to be 3. Now it's important that you always look to see if you have three similar right triangles or you have an angle bisector, because they look similar, but they're not the same. No pun intended. This is the end of the video. You can now start your homework.